Alright, in this video we're going to talk about another vector differential operator, which is called the curl of a vector field. So basically the curl is defined as the cross product of the del operator with respect to the vector field. So we have a cross product, which we know from vector algebra is defined as a 3x3 determinant. So in the top row you have all your unit vectors pointing along each of the x, y, and z axes. Second row you have the elements of the del operator, which are the first derivative with respect to x, then with respect to y, and then z. And then finally in the last row you have the components of your vector field f. So you have x component, y component, z component. Now if you remember how to perform a 3x3 determinant, the idea is that you get the first element here, and then you're going to multiply it by the determinant of the 2x2 determinant of the elements are diagonally across from it. So basically you're going to take this determinant here, and then you just cross multiply the terms and subtract them together. So for the first element you're going to get this difference here, so you're going to multiply this by that minus this by that, so you get this. Second element, remember with determinants we alternate, so we start with a plus on the first element, then minus, then plus, then minus, and so on. So the second element we need to put a minus in front of the j vector, and now we're going to have this term times that term, which is here, and then this times that. And finally for the kth term we do the 2x2 determinant of these four elements here, so we're going to have this times that and then this times that. Now if we can rewrite this in shorthand notation by using the angle bracket notation, all we need to do is just put it in this form. If we carry out the multiplication of that negative sign inside of this element here, then we just basically just swap them around, and then we put the last one here. So it turns out that the curl of a vector field gives you another vector field. So what this actually represents in both a mathematical and kind of a physical sense is that it represents the amount of rotation that is happening about a point in space. So you can imagine that if you were to model something like the velocity field of a moving fluid, then what the curl of that velocity field will give you is the amount of rotation that is happening on that fluid. So if you were to place a particle somewhere here, then basically that particle will just tend to follow a specific circular path around, and you have things like vorticity and then a lot of effects from fluid mechanics that actually follow this kind of thing. And you will see this later on also in electromagnetism. Maxwell's equations have terms that depend on the cross product, or essentially just the curl of a vector field, to define how those rotations relate to moving charges and so on. So this is a concept that is widely used in physics. So this is the main reason we need to learn it. And it also happens in some other fields I will explore a little bit later on. So just to give you an example of how the curl of a vector field is calculated, let's say I give you the vector field. Let's do a simple one first. So let's do x, y, and z. Now the curl of this vector field, well, we can simply use the formula that is given here. So we have this kind of general result here. So basically we're going to take the z component, which is this third component on the vector field, differentiated with respect to y. So this is going to be 0. And now here we're going to subtract. We're going to differentiate this particular one here with respect to z, so that's also going to be 0. Now here we're going to go for this differentiated with respect to z, so that's going to be 0. And then this one is going to be 0. And then it turns out that everything here is just going to be 0, as we can clearly see. So this is just going to turn out to be 0 all over, or we can just simply write it as 0. Now whenever the curl of a vector field is equal to 0, we say that the vector field is conservative. So this is just a definition that is given to the vector field. Any vector field that is conservative will have a curl equal to 0. And this is quite an important concept, because once we start talking about integration involving vector fields, this is actually something that provides a means for calculating things like line integrals and surface integrals, and it makes calculations a lot simpler along the way. So we will come back to this later on when we actually require it. But for now, let's just do another example because I believe this one was a bit too easy. So let's do something a little bit more complicated. So let's do the following vector field. Let's have x squared, y, then e to the minus x squared, and then set x plus y. Okay, so now let's compute the curl of this vector field. So let's say what we get. Alright, so let's see what we have here. So we are first going to differentiate the third component or the set component of this with respect to y. So that's going to give us 1. And now we're going to subtract the component here, differentiate with respect to z, which is 0. Now here we're going to grab the x component, differentiate with respect to z. So that's just going to be that. And then we're going to differentiate the z component with respect to x. So this is going to give us, so z component with respect to x, this is just z. And then finally, we're going to have the y component, so which it's this one here. So we're going to differentiate with respect to x. So this is going to be minus 2x e to the minus x squared minus this differentiate with respect to y, so this becomes x squared. And now if we just simplify this a little bit, let's see what we get. We're gonna have 1 minus z and then minus 2x e to the minus x squared minus x squared. Sorry, it should be plus x squared here. And then if we take the minus out, we can rewrite this as minus 1 z and then 2x to the power of minus x squared plus x squared. And that should be it. So this is going to be the curl of that vector field, and you notice once again that this is actually a vector field in itself. And that's not at all surprising, because if you recall from vector algebra, when you had the cross product between two vectors, so let's say a and b, you actually get another vector which turns out to be perpendicular to those two vectors. So a similar kind of thing is happening here, but now you're taking derivatives with respect to that. So in essence, even though you technically have a vector field that results from that, the relation is just not as obvious. So we need to have some more physical insight into what this is actually doing. But as you will see later on, once we start doing some integration with vector fields, these operations of the divergence, gradient, and also the curl of a vector field are going to come in quite useful.